Hey guys, welcome back. I'm starting a new series on YOLO object detection models. You all know there are many versions of YOLO released, the latest being YOLO v7. In this series, we will go through each YOLO model one by one in detail. We will understand the minute details and question every design choice they have made. So it will be a bit lengthier video here. Please feel free to jump through the timelines to the module that interests you. I will try to make it as simple as possible and make you understand using diagrams. So without any further delay, let's dig into YOLO version 1. Just a bit of background. As you all know, in object detection, we identify the category of the object along with the location. The locations are represented by bounding boxes and the category information is represented by probability scores. If you see this picture, these are only bounding boxes. There is no class information here yet. And here we have the class information. There are few object detection algorithms before YOLO like RCNN, fast RCNN. These are two-stage networks. They generate the bounding boxes first and then they classify the boxes in the second stage. If you see this image is passed through the CNN block, which we call it as backbone, and then it will produce the convolutional feature map. These contain high-level semantic information which are useful for detection. Now in two-stage networks, the boxes are predicted first. One of the example is using RPN. RPN produces the boxes at this stage. We still don't know the category of these boxes. In the second stage, we use the same feature map here for getting the class and bounding box information. So we will get the class probability scores in the second stage. Along with that, whatever the boxes we got here, these boxes will get slightly refined to fit the objects properly. There are many drawbacks for this approach. One being a multi-stage approach. End-to-end single training is not very convenient here. Also, these networks are very complex and not useful for real-time applications. If you consider faster RCNN, it hardly gives 5 FPS on GPUs, which is not feasible for production. And one more drawback is, these are not very generalizable to other domains. This point we will come to later when we are comparing with the YOLO at the end. The idea of YOLO is to have a single network for object detection, doing box prediction and the category prediction in a single shot. So YOLO reframes the object detection problem as a single stage regression problem. When you say regression problem, all the losses we are calculating here are regression losses. Now let's see what happens in YOLO step by step. First we will take the input image, whatever resolution you are having. I am having an example of 640 by 480 here. This image will be resized into 448 by 448. This number is fixed depending on the model architecture choice. So they have decided with 448 resolution. Now divide this image into S by S grids. So in paper they have selected 7. So the image is getting divided into 7 by 7 grids. And each grid has 64 pixels because 448 by 7, it will give you 64. So that means whatever grid you are having here, each grid, it has 64 pixels in it. Each cell predicts one bounding box. Okay. Each cell is responsible for predicting one object. What do you mean by responsible? How do I know which cell should predict which object, right? In my example here, I have two objects. One is person, another one is horse, right? So how do I tell that which cell is responsible for detecting person and which cell is responsible for detecting horse? How does this cell relates to this person predictions? Very simple. The cell in which the object center falls is responsible for the object prediction. So if you observe here, the person class, which is having the blue box, the center is here and this falls into this particular grid cell. Now this grid cell is responsible for predicting the person, and the same way the horse center falls into this particular grid cell. Now this grid cell is responsible for predicting the horse. Again coming back to the same question, what do I mean by responsible? Okay, now I understood that this center falls into this grid, so this is responsible for predicting the person. But what do I mean by that? So for that we need to understand how the targets are getting calculated for training. Once we divide the image into 7 by 7 grid, we are saying each grid cell is responsible for getting one prediction. Now each cell has its own targets. Okay, every cell has its own targets. Here target means the values which we compare with the network predictions. Target means the values which we compare with the network predictions for our loss calculation. In simple terms, targets are what we need to predict from the network. The network training should be such that the predictions and the targets are close to each other, right? So whatever we are going to predict from the network, those should be our targets. So how are these targets getting calculated? So if you see this, these are my ground truth values for the person class. Whatever the person box I am having it here, for this particular box, these are the ground truth values. Now these ground truth values are at the image level, and my target should be relative to this grid cell. What do I mean by relative to this grid cell? Why should I take the relative values? Instead of predicting the object coordinates as the absolute values, we always predict as the relative values, because this makes the training process easier. See, if I want to predict this person, the network has to predict this 200, 311, 140 to 250. These are very big values, right? These are not very easy to predict from the network directly. So if we make the predictions smaller by somehow and then decode them later, that should be better. That's what we are doing it here. So instead of predicting the values directly like this, we are actually predicting the values which are relative to this grid cell. So if you see this delta x, delta y, delta w, delta h, these are actually the targets we are calculating, okay? And this x and y are these values, and this w and h are these values. Now what I am calculating is, from my ground truth value, I am trying to calculate the targets with respect to the grid position. So if you see XA and YA, these are the top left point, which is this point of this grid. So this is the grid, and for this grid, this is the top left point. So I am calculating the relative values of this center point with respect to this grid point. So what I am doing here is, I am just calculating the distance between them. We are just calculating the distance between the object center and the top left coordinate. What does this indicate? This indicates that from this top left corner, how much I have to go in x direction and how much I have to go in y direction to reach this point. That is what we are doing with these delta values. So these delta values are this distance. This is delta x and this is delta y. So these are the values which we are calculating here. The same way, width and height we are calculating with respect to the image level. So the whole image is 448 by 448. So I am just normalizing these values by 448. Hope you understood this. If you don't understand, this example should clear your doubts. This green box is our ground truth. Now the center falls into this particular grid cell. Now this grid cell is responsible for the prediction of this box. Now if I want to calculate delta x, what I need to do is, whatever the x value I am having in my coordinate center, and this x value for the top left corner, I have to subtract. And I am dividing by 64 because each grid cell has 64 pixels. So I am normalizing the value so that it will be between 0 and 1 always. Same thing I am doing for y coordinate, 311 minus 256 divided by 64. And then we have width and height. Width is 142, height is 250, right? And these I am directly dividing with 448 because this is with respect to the image level. Now if you see what we have done, we have actually converted the original ground truth values, which are in the absolute values, into relative values with respect to this grid cell. These are my targets. Now this is for one grid cell. We calculate this in the same way for all the grid cells. Some grid cells might not have any object, right? So if you consider this previous example, only 2 grid cells has objects. All others doesn't have any object. So what happens in that case? In that case, the targets will be all zeros. These A1 to A49, okay, 7 by 7 to we have 49 grid cells. For each grid cell, these are the target vectors. I am assuming only A11 and A32 has objects. All the remaining grid cells doesn't have any object. All these grid cells have zeros. Only A11 and 32 has some values, because if you have an object in that, then you will have the box coordinates, 4 values, followed by the confidence score. So we have seen how to calculate these targets for the box coordinates. But what about the class probabilities or objectness score? So generally this has 5 values. The last one is objectness score. So if you see this example, if this is assumed that it has an object, then the objectness score will be 1. Otherwise it will be 0. And if it has an object, it should have a class assigned to it, right? And if it have a class assigned to it, generally the class values we represent using one-hot encoding vectors. That means if my dataset has 20 values, like Pascal VOC here, 20 classes are there, I will take a vector with 20 values and then I will keep all the values 0 except the one position where the actual class is, that will be 1. Let's suppose this A11 and A32, you take this one. I'm assuming that the 14th position is the person class in the Pascal VOC. Let's assume that. Now all the other values will be zeros. Only the 14th position will be 1. Same thing here for A32. This particular object also I am assuming as person, and so 14th position. This is actually 14th position. The 14th position will be 1. All others will be 0. So that's what actually we call one-hot encoding vector. So if you observe, these are all the target values for all the grid cells. So for all the 49 grid cells, we have the target values here. Now we understood the target values. Now let us understand the model output, because for loss calculation, we need to compare these two only, right? Model output with the targets to get the actual loss value. So let us understand the model prediction. So from the model side, each cell will give 2 bounding boxes. Okay, earlier we mentioned each cell will predict only 1 box, but here we are saying 2 bounding boxes. Let's see that. We'll come to that. So each cell will give 2 bounding boxes, and for each bounding box, we have these deltas. These are the deltas for the box coordinates, and this is the class objectness score. Okay, there is no class information here yet. It is only objectness score, which will indicate only whether that particular box is an object or not. It has an object or not. How much confident the model is that this particular cell has an object. So if you see this, the first two are offsets to the top left corner, right? These are actually relative to top left corner of the grid cell. And these delta W and H are with respect to the total image, and the C, which is the probability that the box contains an object. This still doesn't know what class it is, what category it is. It only knows that it has an object or not. And then we have the class probabilities. So the class probabilities, we have 20 vector, because for Pascal VOC classes are 20. Now these will be the prediction values, which will be between 0 and 1. Right? It can be 0 also, 1 also. The number of parameters, all these we are discussing is per grid cell. So the number of parameters per grid cell are, so these 5 values for each bounding box. So 2 boxes are there and each has 5 values here. Okay. So this is from here, and then plus 20 class scores. Total gives me 30 values. So for each grid cell, we are getting a vector of 30 values. For our actual model, we have 7 by 7 grid cells, total 49 grid cells. So 7 by 7 into 30. This should be the output coming from the network, because for each grid cell it is 30. For 7 by 7 grids, it is 7 by 7 by 30. So if you see this 7 by 7, these are the grid cells, and the first 5 values are for one box, second 5 values are the second box, and the next 20 values, these are 20 are the class probability scores. Here is an interesting point. We have 2 boxes here, right? So box 1 and box 2, but we only have single set of probability scores, right? Only 20 probability scores, which is a single set. Now if I have only one, that means it is actually independent of the boxes. So as I mentioned earlier, each cell is still responsible for only one box. The end output will be only one box. Even though we are getting 2 boxes here, we will only keep one of them. Which one to keep? So generally we keep the box with the highest confidence score. So we will see that in the post-processing slides in the next one. Now we have got this prediction vector, right? These deltas we got and the probability scores we got. Now how do we parse these things? So I'm getting 7 by 7 by 30 here, and from that first 5 are the deltas for one particular box, and the next 5 are deltas for the second box. Now these deltas we are having, but how do we use these deltas to get the actual vector? If you see this, my person box is this one, right? This is my person box. Now how can I get this box from these deltas? These deltas are all between 0 and 1. All these values are between 0 and 1. How do I use these values to get this particular box here? That is using this one. If you see this, these deltas are being used here. XA and YA are the grid cell top left corner. So if you see, 2 boxes are there for the same grid cell here. Same grid cell, 2 boxes are there. So with the same corner, top left corner, we calculate 2 different boxes. So this X1, Y1, W1, H1 are for the first box. Let's assume that that is for the red box here. Okay. And this one, this X2, Y2, WH2 are for the blue box here. Right? Let's assume that. Now we got the 2 boxes for the same grid cell here. So these are for the box values. Now we are left with the confidence scores and the class probabilities. So let us see how to use them. So the confidence scores, usually we take C1, C2 as it is, okay? And from the probability scores, we take the maximum of probabilities, all the probabilities, that is my class probability, final class probability. So I have 20 classes. Let's say I got the person class here, which I assumed as 14th position, right? So for 14th position, I got the probability score as 0.8. And for the remaining all, it will be smaller values because the sum of them should be equal to 1, right? Sum of probability should be equal to 1. So this one is the highest probability, maximum of this. So this will be 0.8 here. So this 0.8 I will multiply with confidence scores of both the boxes. This box has one C1, this box has C2. So I am multiplying that with the confidence score, which is my 0.8. So this is my 0.8 here. Now I will get the final confidence score, which is called conditional confidence score. Conditional class probabilities or conditional confidence score, because this value is based on confidence of an object existence also, not only the class probability, it is based on the object existence also. So these two are the final confidence scores. Now out of these two boxes, I will only keep the box which is having the highest confidence score. These two boxes are there, but I got highest confidence for the blue box, right? So I will only keep the blue box. I will actually discard the red box. So even though model is predicting two boxes, we are only keeping one box at the end, which is having the highest probability score. Okay, this is what is happening in the post-processing. So far we have seen how targets are calculated and how the predictions are parsed to get the final objects. So what we have done, we have divided the image into 7 by 7 grid, then pass it to the network. We don't know the network, but we will see. Let's assume that we pass it through the network and we got the bounding box coordinates, deltas, and the confidence scores, from which I parsed the original coordinate values. Along with that, I got the class probability scores, and finally I combined those two to get the final bounding boxes. This is what we have seen so far. Now let's see the architecture. Architecture is pretty simple. It's all convolutional and max pooling layers. If you see this architecture, everywhere you see convolution, max pool, all convolutions, max pool. So there is no other layer available in the network. All are convolution and max pooling layers, nothing else. Just the combination of those two. So this network is actually inspired by GoogleNet design, and it has 24 convolution layers. The total block, whatever you are seeing here, this is 24 convolution layers. Okay, along with the max pool layers in between, and we have additional 2 fully connected layers after these 24 layers. Now these 24 layers we can consider it as backbone. I'm saying this, introducing this nomenclature so that these will be used in the later lectures also. So usually the backbone will be always having mostly convolution and max pooling layer combinations. It will not have fully connected layers. It is actually used for generating the feature maps. Okay, on top of these feature maps, you will have the further layers to get the predictions. This is the backbone we call it, and this backbone ends here with 7 by 7 by 1024. So the final layer will be 7 by 7 1024. If you flatten this, then you will get 50176 feature vector. It's a single vector, 1 by this one. Why should I flatten this vector? Because to pass through fully connected layers, we should have a single vector. We cannot pass the block directly to the fully connected layer. So that's what we are doing here. 7 by 7 1024. This is the output from the backbone. From that backbone, we are flattening into a vector and then passing through 2 fully connected layers. Okay, one fully connected layer is converting this 50k values into 4096. And then another fully connected layer converting the 4096 to 1470. And this 1470 values are actually my final vector. So this 1470, you can actually reshape it as 7 by 7 by 30. This 7 by 7 by 30 is actually what we have seen here, right? This is this 7 by 7 by 30 vector. So that is our final network output we are getting, and we already saw how to parse that to get my final predictions. This is the total architecture. You are passing 448 by 448 image, and then 7 by 7 grid cells you are dividing. From there all convolution max pool combinations, and then finally you got 2 fully connected layers to get 7 by 7 by 30 block. Now let us see the training process. As I mentioned earlier, the training, it has used Pascal VOC dataset, which has only 20 classes, and the network is actually pre-trained on the ImageNet dataset at 224 by 224. Okay, so the ImageNet pre-training is actually for the classification task. It's not for object detection. Usually pre-training is performed to make the model learn features that are useful later, right? So this will actually reduce the training time of your actual detector. So this will learn very useful features, and imagine it is a huge data set. It will have all the objects which you are going to see in your Pascal dataset already. So it might have learned all the features of how a cat looks like or a dog looks like, even though it doesn't know the localization at that moment, but it still learns the features. And then those features will be useful later when you are actually training on the dataset. So generally this is a common practice. It's not mandatory, but it's a common practice to pre-train any of your custom model, whatever you have developed, let's say, that custom model on very big dataset for classification task, so that it will learn the features, and then you will actually fine tune that model on your actual dataset, right? So in this case, imagine it is the biggest dataset for classification we have got so far. So we train the model on that imaginary dataset and then get the better features. Those features, that trained model, we actually fine tune it on the VOC dataset. And then what they have done is, imagine it, they have trained it 224 resolution, and then for object detection they have increased the resolution, because for object detection, generally for localization, you need better resolutions. So this is the training process. So you take the Pascal VOC dataset here and you randomly select some of the dataset. Okay, so here, even though I am representing as an image, from this particular path we are only taking the ground truth labels. So that label encoding is that process I have explained, this one. Whatever the coordinates we are getting, we are actually converting into relative coordinates with respect to the grid cell. This is actually called label encoding process. And once I got the labels encoded, then I am passing to the loss function. Okay, this is one branch. We got it ready here. Let's keep the labels here. Then the actual image is passed through the YOLO network, and then you got the 7x730 predicted map. Now these predictions are actually compared with these labels to get the loss computation. Now this loss we have to reduce so that you will actually back propagate and then update your parameters. So this is the total process. So here only labels are getting passed. Here the actual image is getting passed. Both are getting compared here, and then adjusting the parameters so as to reduce this loss value. Okay, that's the total training process. Now let us understand the loss function step by step. So we calculate the loss for every grid cell. We have predictions and targets for each grid cell, right? So these individual losses are summed together to get the final loss. So these grid cells might have objects or might not have an object. So objects are important to us. So what we do is, we put more importance on the grid cells that contain objects, decrease the importance of grid cells that have no objects. If you see this example, right, our example, we have only 2 grid cells with the object. All remaining 47 grid cells, there are no objects in it. So if I give equal weightage to all the cells, then this no object loss will dominate the loss of the actual objects. So what we do is, we decrease the importance of grid cells having no objects. So that is what we are doing it here. We are actually splitting the loss function into 2 parts. One is the loss for the grid cells having an object, and one is for grid cells not having an object. Okay, and for grid cells not having an object, that particular loss value I am downgrading by using 0.5. So this is a lambda new parameter. This parameter is used as 0.5 in the paper. So this is actually to reduce the importance of this particular loss when there is no object. Now these two components are mutually exclusive. This is the loss for objects and this is the loss for no objects. So any grid cell will have either an object or not, right? It cannot be both. So if these terms are actually the values which will become 1 if the object is there. So if this value is considered, this will become 1 only if the object is there. This will become 1 only if there is no object. So other cases they will become 0. So that indicates, even though there are 2 terms here, for each grid cell only one of these will be calculated. So this is just the mathematical representation of that. Now let us break the loss function for the cells which have objects. So if I have an object in a particular grid cell, then what are the components it will have? It will have the box coordinate values, it will have the objectness score, and it will have the class probabilities, right? Now the paper, they have actually put more weightage on the box coordinates compared to the other 2 scores, because those are probability scores and box coordinates are actually real values. So they have put more weightage on the box coordinates. So the total loss of a grid cell where an object is there, it will be loss for the box coordinates, loss for the confidence score, loss for the probabilities, class probabilities. So the combination of these 3. Now we will see one by one. So as I mentioned, they have put more weightage for this one. So they have added another parameter here before this box loss, and that is actually kept as 5. Now let's see the box loss in detail. Don't confuse by these terms, don't get scared. This is actually the ground truth. These are the deltas which we calculated, the targets, okay? And these are the predictions from the model. So both are delta values. Both are ranging from 0 to 1. Now what we are doing in the loss is just the square root difference, okay? Difference between them, difference between this and this, these two, and then square it. Difference between these two and then square it, right? And then W square it. H and H square it. Only difference is the W's and H has the square root term here because they can vary in high values compared to the X and Y, right? W and H are actually with respect to the whole image, not with respect to the grid cell. So the values can be varying in higher values compared to X and Y. So this particular square root term here actually it downscales the high values, whereas actually low values will still be less affected, right? This is actually kind of a weighting factor we are adding here. That's it. And next comes the objectness score. Objectness score is actually confidence score that indicates that that particular cell has an object, right? So this is, if an object is there, definitely the target is 1.0 as we have seen earlier. The target is always 1 if the object is there. And the predicted value can be anything between 0 and 1. So let's say this particular grid cell, it has predicted that it is 90% confident that it is an object. So we just take the square root difference here. So everything is square root difference in YOLO V1. You need not to worry about other loss functions. Everything is square root difference. That's why they have termed as regression. So the whole object detection they have reframed as a regression problem. So it's a square root difference. And then let's see the class probabilities. Class probabilities also, if you see this one, this is the ground truth and this is your predicted classes. Ground truth is actually one hot encoding vector which is having 20 values, right? The same way this also 20 values vector. So now each value we have to subtract from each other and then take the sum of all the 20 values. So that's like this. So the first value, take the square difference, second value square the difference, like that. For all the 20 values, take the square difference and add them here like this. If you take an example here, like I have taken earlier, like 14th position is a person. So for that the target is 1, all others will be 0, right? And for that position, my prediction has 0.8 confidence score. For all others, it has some different values, which are very, very less. So this is how the difference will be calculated. 0.8 minus 1 for the 14th position. And remaining whatever the values we got, we will actually difference with zeros. So finally, we get the final loss value as a single value like this. So this is actually for each grid cell, it happens like this. All these values. For each grid cell, these things happens. Now what happens if there is no object in the cell? Okay, so far we have seen 3 types of losses for the grid cells where there is an object. These are the 3 types of classes. Now if I don't have any object in a particular grid cell, what should I do? If I don't have any object, there won't be any boxes or there won't be any class probabilities. The only loss we will calculate is objectness score loss. This also, the targets are always zeros because there are no objects, so targets is always zeros. Only your predictions can have some values between 0 and 1. Now you have to reduce this loss so that the grid cells which doesn't have any object should not give some confidence score that it has an object. So the only loss we calculate no object cells are only the objectness score. Okay, this is also the square root difference only, nothing else. So this is the total loss function. So it seems big here, but you can see that we have went through portion by portion and those are all very easy terms actually. So if you see the initial, these are square root difference for X and Y, square root difference for width and height. Okay, this total is actually bounding box coordinate loss, regression loss, coordinate regression loss. And this particular value is 5 because to increase the weight of these things. And then we got the confidence score loss, okay, objectness score loss you can say, and these are the class probabilities loss. All these are square root differences, okay. And these 1 here you can see these will become 1 if there is an object here, and this will become 0 if there is no object in the cell. So that means for a particular grid cell, either this component will get evaluated or this component will get evaluated. So this is for the grid cell which are having an object, and this is for grid cell which is not having any object. So this is also no object, this is downgrading, so this is actually 0.5 weightage we have given, and this is also becomes 1 when there is no object, and this is square root difference again. So even though it looks pretty complex, it's very simple loss function. It's the simplest actually because it's all square root terms. Now There is actually a lighter version of this model which is called Fast-YOLO. So instead of 24 layers in our backbone, they have reduced to 9 layers, only 9 layers. This is only for the purpose of getting highest FPS, faster FPS, and see how much performance we can gain. So now that we have covered both the training process as well as the inference part, right? So we have covered the targets, how do we actual step-by-step process, what do we do in the YOLO, and we have covered the target calculations, the ground truth values, and then we have seen the output vector and how to parse that vector, the loss computations we have seen, the training process, how it happens we have seen. So that pretty much covered the whole YOLO. Now let's see its performance. So you can see that YOLO is the fastest model in the whole chart. So 155 FPS, there is nothing even nearby. So 100 FPS it is there, DPM, but this accuracy is very less. 16 MAP, here it is 52, 63, right? So this is the fastest model. You can see that if you observe the real-time detectors, which are actually useful in the production use cases, YOLO is the highest, having the highest accuracy. There is nothing to beat it. But if you compare with the faster CNN versions, right, then you have the models with a good amount of accuracy difference. So 63 is the highest we got here, and 73 is for faster CNN VG16. So almost 10 MAP difference. But if you see the FPS, 45 FPS and 7 FPS, right? So you can see how much faster YOLO is with the 10 MAP difference. So you can see the same difference here. 65 correct predictions and 71% correct predictions. But there is one observation here. You can see this background 13.6%, that indicates false positives. The fast RCNN model is making more false positives compared to YOLO. Even though the correct predictions are less, there is no false positive. I mean, there are less false positives in YOLO compared to fast RCNN. Also, the others have done experiments to validate its generalization capability. That means how easy to adopt this network to other domains. So they have tried evaluating the model on Picasso as well as the PeopleR datasets, and they have observed that actually this is adopting, YOLO is adapting to other domains much better than the fast RCNN or fast RCNN, those two-stage networks also. This might be because we are actually looking at the whole image at once, right? It's not like, okay, if you observe the fast RCNN or stage networks, we don't see the whole image when you are actually calculating the class probabilities or box regressions. We only take a portion of it. We only take the boxes coming from the RPN, and those features we take for the class predictions. Whereas in YOLO, it's the total image it is actually looking at for the even the box and class probability. That might be one thing, that it has better context information, which might be one of the reasons that it has less false positives here. That tells us one reason, and it is well adapting to other domains also. Well, there are few limitations for YOLO also. So one, we have already seen that accuracy is very less compared to two-stage networks. 10 MAP difference is very huge. And one more thing is, each grid cell can only predict only one object, right? That means only maximum of 49 objects it can detect from a particular image, because we are dividing into 7 by 7, right? So it's a very big restriction. If there are very crowded scenarios, like people side by side, then there are chances that in a single grid, right, if you observe this one, like this is my total image, okay, these are my grid cells, like this is my one grid cell. So here I have like 4, 5, 6 objects are there in a people group. Now because of this limitation, out of these 5, 6 boxes, only one particular box, actually not even 5, 6, only 2 boxes we are predicting, and out of that we are taking the one box with the highest confidence score, right? So even though we have centers, object centers available in this grid cell of 5 or 6 groups, but still we can only predict one from that, right? That is actually one limitation. So it cannot, if you have very close groups, people close to each other, then there are chances that all those coming in a single grid value, right? Single grid cell, and which is actually restricting to predict only one of them. That is a drawback. And also they have observed that it has actually poor localization. So that means that the box which is actually getting predicted, that is not properly enclosing the object, right? It might not be a very good fit for the object, right? So that can be one thing, like we are always having a fixed size here. Grid cell is a fixed size. Okay, there is something called anchors concept which will come later, but there are no anchors here. All these are fixed grid cells, and whatever the box size is, like this box size is like this, right? my grid cell is only this. My grid cell is only this, but I have to predict this box size. See how much difference it is. So it has to traverse from this to this, right? All these it has to predict. So it might be different. So because of which the localization might be poor, and this problem, especially this will be solved by considering the anchor points, anchor boxes, which was adopted in the YOLO v2 version. So yeah, this is all about YOLO v1. Hope you understood the concepts clearly. Let's meet again for becoming better, faster and stronger with YOLO v2. So thank you guys.